In this section, we are going to see applications of TF IDF. So, interestingly, just a basic algorithm like TF IDF can already solve quite a few NLP problems, ranging from extracting keywords to summarizing documents to finding similar documents and other things. Let's look at a few applications. So first, let's start with extracting of keywords. So just to understand on a high level, how do you extract keywords? So if we assume keywords are important words in a document, in our case important words from a movie plot, essentially we get all the words in a movie plot and we get TF-IDF value for all the words in the movie plot. And then if we just sort them by descending order of TF-IDF values and get the top n high value TF-IDF words, essentially those are the keywords. Let's for example take a different movie, V for Vendetta. So here I have V for Vendetta movie that I just printed. So let's run this first and see what exactly these lines do. So first of all, we are using our TF-IDF vectorizer that we already did a fit on. So what happens is that once you do fit on the whole corpus of movie plots, all the unique values, that is the features, are already extracted. Here in our case 48,000 plus. Then IDF for each feature or word is also extracted. So once fit is performed, IDF values are calculated and the features are extracted. Features are the columns basically, or the words. Now what we did was, here we got V for Vendetta movie plot and we are passing it through the previously fit defined TF-IDF vectorizer by calling the transform function. So once we call transform, essentially what's happening is just TF is calculated for this movie plot and previously calculated IDF values are multiplied and TF-IDF values are extracted. So that's what we are getting for this movie plot. And here we are initially printing the feature names that we already have. I just added this line as well and reran. So essentially we have feature names, that is the 47,000 or 48,000 columns, and simply once we call the transform on this movie plot, we are getting this movie vector. So we can convert that movie vector into an array and we can flatten it. So if we just flatten it and print it here, it's clear. So these are the values that you can see. So this is the movie vector array that is flattened once we did the transform. Although most of them look like zeros, there are some values that are non-zero, and as you can see, the length of this vector is 47,864. And what we are doing in these two lines is sorting the indexes by descending order of their values. So if you see this movie vector array, there are some non-zero values obviously, and we are sorting it such that we are getting the indices, that is the index of values that are non-zero and sorted in descending order. And we are using the sorted indices to get the actual words from the feature array. So as you can see, EV, Creedy, Northfire, Sutler, Larkhill, these are the keywords from our movie V for Vendetta, EV, Hammond, and all the words. And we are also correspondingly printing the TF-IDF scores, because you can just flatten and get the corresponding values from that flattened array with the sorted indices as well. So although it looks a little bit cumbersome, what's happening is quite simple. We are getting the TF-IDF vector for this movie plot. That's what this is. And these are the features corresponding. Now we are sorting this array by the decreasing order of values, that's in here, and we are getting the corresponding words from the feature array, that's in here. So at the end of the day, from this movie plot, we extracted the top high valued TF-IDF words. We just printed that here. These are the words from this movie that have the highest TF-IDF values, and they are assembled in decreasing order. That's about it. And that's how we extract keywords. Now the thing is, as I mentioned previously, you can create TF-IDF vectorizer with n-grams that could be bigrams or trigrams even, and you can extract here bigrams and trigrams. So then you can extract names even that might be bigram names or trigram names, etc., like E.V. Hammond, Lewis Prothero, etc. So it's not just limited to unigrams, but I'm just mentioning you can even do it for bigrams and trigrams and extract the high valued TF-IDF bigrams, trigrams, and sort them as well. Let's move on to how we can summarize any document. In our case, how do we summarize a movie plot using TF-IDF? Simply, a collection of keywords makes a key sentence, and a collection of key sentences makes a summary. What I am trying to say here is that in every sentence of the movie plot, if you try to calculate the average TF-IDF score, because a sentence has words and each word has a TF-IDF score. So if you just take the average TF-IDF of the sentence, if you just get the top n sentences that have the highest average TF-IDF score, and if you sort them in the order of appearance in their movie plot, that's basically the summary. Let's look at it. So in this case, let's take Batman Begins. You have the movie plot here. So here I'm just using NLTK library to do sentence tokenization. What that simply means is that if you just give this text as it is to NLTK library, it will automatically split it into sentences and print all the sentences. That's what this is doing. So Batman Begins, if you just print everything, there are these many sentences. Now summarization means essentially you will get the average TF-IDF for each sentence, and you will get, let's say, top 10 sentences from this which have the highest average TF-IDF. That's basically the summary. Here we are doing extractive summarization, which is we will just pick sentences directly. If there are 100 sentences, we'll pick the top 10 sentences directly to show it as the summary of the movie plot. So it is called as extractive summarization. Whereas abstractive summarization is actually rewriting in few lines in own words. So kind of like paraphrasing and rewriting, not just writing the sentences as it is, but rather rewriting them. But in extractive summary, all you do is just pick the top sentences, and the sentences directly come from the original movie plot or document. So what we are doing here is interesting in the sense that for each sentence we are getting the TF-IDF vector, and that's what we are doing here. Once you run this, you will get the TF-IDF vector, the whole vector for each sentence. And let's run this to understand what it does. What this code is doing is kind of similar to what we have seen previously, which is for every sentence, what we are doing is just we get the TF-IDF for each word after removing the stop words, and we are getting all the non-zero values from the TF-IDF vector and then sorting them in reverse order in their decreasing order of values, and we are just summing all these things and dividing by the total length of the sentence, so that we are normalizing the score. So at the end of the day, this is a score that we get, and it's basically the average TF-IDF score of this sentence. Since each word has a TF-IDF, for example, Gotham has this score, and similarly bats has this score 0.3875. At the end of the day, all we are doing is, for this sentence, we are extracting the TF-IDF vector, and we are just summing up the TF-IDF scores of all these words and then dividing it by the total number of words in this sentence. So it's kind of like an average TF-IDF score for this sentence. And let's run this and this cell. And once you run this, you will realize that all we did was to sort the sentences by their average TF-IDF score. So for example, Batman Begins has 100 sentences. In the above cell, we calculated average TF-IDF score for each sentence. And in here, in these two cells, we just reordered the sentences based on their average TF-IDF score from highest to lowest, as you can see. But here we are printing every single one of the sentence. Now what you can do for summarization is, let's say if you want to summarize it in 5 sentences, you take top 5 sentences, and then within the top 5 sentences, you will just rearrange them such that their order of occurrence in the original movie plot is preserved. So if you want to summarize the whole movie plot into K sentences, you will take the top K sentences, then again reorder them in their order of occurrence in the original movie plot. That's it. That's how you do summarization. Now moving on to similarity search. What we are going to do here is actually get the Batman Begins movie plot, and we are going to find similar movie plots and print them from all the 3,300 plus movie plots that we have. So this is a Batman Begins movie plot, and I know that the index is 60. And again, our TF-IDF vector for our search query, which is our Batman Begins movie, again we are using transform output. Since we have already calculated our TF-IDF vector, as you can see, transform output is this matrix, TF-IDF matrix of 3379 by 47864. So we already pre-calculated TF-IDF values for all the movie plots. All we are doing here is that Batman Begins index is 60. So we are going to just get the 60th index vector. So this is a vector of 47864 dimensions, and this vector is TF-IDF vector of Batman Begins movie plot. Now what we are doing here is we are initializing a linear kernel to calculate cosine similarities between the Batman Begins TF-IDF vector and all the values in this, which is all the movie plots. So we are getting cosine similarity. So cosine similarity is nothing but a similarity metric between how close two vectors are each other. So transform output has vectors for all the 3,379 movie plots, and search vector has the TF-IDF vector of just the Batman Begins movie plot. What we are going to do is compare this with all the movie plots and extract cosine similarities. So the one that has the highest similarity is the movie plot that we want. So these are the cosine similarity values. So this value stands for cosine similarity of Batman Begins with the 0th movie plot. This is with the first movie plot. This is with the second movie plot, etc. And again, what we are doing here is just get the top 10 cosine similarities and we are going to print them. So essentially what this means is that these are the indices that match closely with the Batman Begins movie. Since this transform output also has Batman Begins, we can see that the index 60th is actually Batman Begins, and when you do cosine similarity with Batman Begins with all the movie plots, the highest cosine similarity comes from Batman Begins itself. So this is a good validation as well to see if we are doing well. Now these are just movie indices, and if you just print these indices and their plots, names and plots, it will be very clear for us. Let's just print this. As you can see, the 60th movie plot is actually Batman Begins. So Batman Begins, when compared to all the movie plots including Batman Begins, the closest one is of course Batman Begins itself. Then the second closest one is actually Dark Knight. Now because all we are doing here is calculating the cosine similarities between TF-IDF vectors of Batman Begins and all the other movie plots, and for sanity's sake we kept Batman Begins as well in the comparison of the others on the other side. So you can see that that's the top retrieved one, and the next is Dark Knight, which is essentially Batman Begins sequel. Then comes Lego Batman movie, and then Batman vs Dracula. As you can see, the search is working well. Great, we have built our very first search engine or recommendation engine where given any movie plot like Batman Begins, you can extract the most n similar movie plots, and you can see that already you are able to retrieve similar movie plots, that is sequel of Batman Begins, Dark Knight, and also Lego Batman movie, etc. So this is the similar document search part. So we extracted similar movies. Just to kind of sum it up, what we did was very simple. We converted Batman's Begins or any query movie plot into a TF-IDF vector. Now we have TF-IDF vectors of all the other movie plots. You are simply doing a comparison with cosine similarity of Batman Begins TF-IDF vector with all the other movie TF-IDF vectors, and you are just sorting them by the highest similarity score, and you know that Batman Begins comes at the top, then comes Dark Knight, etc. Then you might get this question, how do people do sentiment analysis or some classification task as well? Again, that's not too complex. At the end of the day, any text is converted into a vector. So in our case, for example, movie plot is converted into a 48,000 length vector, and you can similarly prepare training data. For example, you have this 48,000 unique vector, then there is a right column which might be action movie yes or no, which is a binary column 1 or 0. So you can have all these 3,500 movies, and for each movie you extract a vector of length, you extract the TF-IDF vector of length 48,000 approximately, and there is a last column which is 1 or 0, whether it's a action movie or not. So now that's your training data, your 3,500 plus movies, and the last column is a binary 1 or 0 label. So you can assume you have 47,000 features, and the last column is a binary label 1 or 0. Now you can train any classifier, machine learning classifier like logistic regression or even deep learning based algorithms just taking these 47,000 columns as the features and the last column as the classification column. It could be a movie genre classification, or it could be even sentiment classification, however you want. So the feature set is basically the TF-IDF vector itself, and that's how you can do any classification task as well if you want. So just a simple algorithm like TF-IDF, using that we have seen how we can extract keywords, how we can do summarization, how we can do similar document search, that is recommendation engine, and we also know how to do classification as well if you want. Thanks for watching, and I'll see you in this next section.